All right, in this video I want to continue talking about the reactions of carboxylic acids and their derivatives. In the last video, the last reaction we talked about is called acyl carbon substitution reaction, and both carboxylic acids and derivatives will undergo that reaction. We showed that there's an overall pattern that applies that assists you in determining the structure of the product. And as well, we discussed the mechanism. And I want to now just review some of the basics with regard to the mechanism. Stripped down to its basics, the mechanism of acyl carbon substitution is fundamentally two steps. Step one, the nucleophile bonds to the carbonyl carbon. This gives this addition a product. If this were an aldehyde or ketone, an electrophile would attach the oxygen and you'd have an addition product. But things are different here because there is a heteroatom group attached, always. That's what L stands for. Heteroatom groups being oxygen, chlorine, nitrogen, sulfur, directly bonded to the carbonyl group. Well, those heteroatom leaving groups now are able to act as leaving groups. Carbon and hydrogen in an aldehyde and ketone won't. They won't come off with their electron pair. But the heteroatom groups will. And so the second step is the ejection of the heteroatom leaving group. Now, because this species that forms in step one is really an intermediate, we call it the tetrahedral intermediate because when the carbon starts out, it's trigonal, and when the nucleophile attaches, it's got four bonds to it. It's a tetrahedral species. All right. Now some important details. Always with any mechanism, one wants to know what the rate determining step is. Well, in this mechanism, step two is generally the rate determining step, but there's an exception. When the heteroatom that's attached to the carbonyl group is a chlorine, that is, the substrate would be an acyl chloride, then step one is rate determining. The addition step is rate determining. And the reason is that chlorine is such a good leaving group. It's the best leaving group of all the other groups here. It's such a terrific leaving group that departure step two, is fast. And that would therefore make step one for it slow. Now, another issue is this. Ejection of that heteroatom leaving group sometimes will be protonated before departure and sometimes not. So we want to look at that. Now remember that the overall mechanism occurs under two conditions: base neutral conditions or acidic. If it's acidic, it's catalyzed by hydrogen ion. Well, if it's under base neutral conditions with respect to the possibility of protonating that heteroatom leaving group, here's the story. The L departs without prior protonation under these conditions, except when the leaving group is nitrogen, that is, when it's an amine group. The substrate would be an amide. And here, the leaving group has to be protonated before departure because the amine group would break off as amidion. That's a very highly basic, unstable anion. It's a terrible leaving group. So if you have a nitrogen group attached, it can't come off unless it undergoes a prior protonation. Under base neutral conditions, now there isn't a whole lot of acid to protonate that. It would generally come from the solvent. Now under acidic conditions where it's acid catalyzed, the rule is that all of the heteroatom leaving groups will get prior protonation before they eject. And that kind of makes sense because under acid conditions there's an abundance of hydrogen ion all around, and so if it's there, it's going to naturally want to attach to that heteroatom group. So the rule is that under acidic conditions, the L will get protonated before it departs, but there's an exception. Exception is when the leaving group is chlorine. Chlorine is so weakly basic. Consider chloride ion mixed with hydrogen ion. They don't bond. I mean, chloride ion is essentially no basic properties at all. So chlorine is so weakly basic, it could never have a proton attached to it. And so protonation of it cannot occur. But all the other heteroatom leaving groups, yeah, under acid conditions, they will pick up a proton before this ejection step occurs. All right, I want to mention that I haven't done it yet, but I'm going to be posting some animations of different mechanisms that we've been talking about here. There's several videos. They're all on YouTube. They're videos that I created some time ago, and I'll post links to those. All right. So let's turn our attention to a different reaction of, well, in this case it would be carboxylic acid derivatives. And the reaction we're going to consider is kind of part and parcel to acyl carbon substitution. That's why I include it here. Well, I want to look at the reaction of carboxylic acid derivatives with organometallic compounds. Now, if you recall, organometallic compounds fall fundamentally into two categories. Category 1, those are the most reactive ones, and they include where the metal is group 1, group 2, the organolithium and the Grignard reagents. And group 2 include all the other metal organometallics, and they're less reactive. All right. Now, first, let's look at a case of a carboxylic acid derivative reacting with a category 1 organometallic. Well, the story is, because they're so reactive, they'll react with all carboxylic acid derivatives, well, except amides. Amides are actually the least reactive of all of the carboxylic acid derivatives. All right, so the general pattern of reaction is, here's our general representation of a organometallic. The carbanion part acts as a nucleophile. It's going to bond to that carbon. All right, makes your tetrahedral intermediate. Step 2, it's going to eject the leaving group here, and we will get an aldehyde or a ketone. Now, assuming additional Grignard reagent, then there is a follow-up reaction. We have, remember, aldehyde ketones will readily react with organolithium or Grignard reagents. So we're using organolithium here, so it's natural that the aldehyde ketone produced here will react with additional organometallic reagent. The G minus acts as a nucleophile. It's going to attach to the carbonyl group. The lithium ion bonds to the oxygen. In other words, this is just the classical addition to a carbonyl group that we studied back in chapter 20. And so you get this addition product, right? Now this is actually a lithium alkoxide salt. I mentioned this before, but in many organic chemistry reactions, the final product is an organic salt. And it wouldn't go any further, and if you wanted to, you could go through the labors of isolating it, purifying it, but nobody does. And generally what we do is we add acid or base, convert it to a neutral compound. In this case, we do an acid workup. We add aqueous acid. Here's an acid-base reaction, H plus protonates the oxygen, and you're getting an alcohol product here. Now, let's see, the next slide show an actual example, make this maybe a little clearer. We're using an ester and a Grignard reagent. Remember, when they very reactive organometallics, they react with all the carboxylic acid derivatives except for amides. And I want to mention that we're not including carboxylic acids here. If we did, it would just be an acid-base reaction, and that would destroy the Grignard reagent, and you'd be done. So we have an ester and the Grignard reagent, ethyl magnesium bromide. That's going to do an acyl carbon substitution on that, producing this ketone. Now, assuming we have additional Grignard reagent, and normally when we do this reaction, you'd have a 2-to-1 mole ratio, twice as much of the Grignard as you would the substrate here. All right, so as long as we have additional Grignard, that's going to affect an addition on the carbonyl group here. Here's the addition product, and it would stop here. Yeah, that would be as far as it would go, but we do an acid workup. Proton protonates the oxygen, and you're getting an alcohol. Notice a tertiary alcohol. We start out with this carbonyl group. We're going to lose the methoxyl. We attach two carbon groups, two ethyl groups to that carbon, and this pattern reaction is always going to give a tertiary alcohol. All right, let's now look at the category 2 organometallics. Being less reactive, they won't react with, let's say, esters and so forth. They will only react with the most reactive, which are acid chlorides. Now, at some point I need to, I'm not sure we're doing it in this video, but maybe the next, that there is a difference in reactivity of carboxylic acid derivatives. For now, just note this, that of the possible derivatives, the most reactive is acid chloride, and the least reactive is amide. That's all I need to know right now. The most reactive is acid chloride, and the least reactive are amides. So your category 2 organometallics, they're WIMPs. They can only react with the most reactive of the carboxylic acid derivatives, the acid chloride. And so I'm going to use diorganocadmium. G represents an organic group. It could be any kind of organic group. All right, so the first reaction basically is here's the ionic form of the organometallic. The carbanion, that's a nucleophile attaching to the carbon, giving a tetrahedral intermediate, which then in step 2 ejects the chloride ion, and you've got a ketone. And guess what? These category 2 organometallics, they're such WIMPs, they won't affect an addition on a carbonyl group of an aldehyde ketone. They just don't. They're not reactive enough. You know, it takes a Grignard or it takes an organolithium, but an organocadmium, nope, that's it. So the reaction is done here. It stops, and you have a beautiful way actually to make a ketone, starting from here at an acid chloride. All right. Here's an example. Here we're using a different category 2. This is, you remember, the Gilman reagent. This is it has kind of the odd structure, but there's 2 ethyl groups bonded to a central copper. In the ionic form, we write break off 1 as a carbanion, everything else is positive. The ethyl carbanion is nucleophilically going to attach to the carbon, and in step 2 it kicks out a chloride ion. And reaction stops here at the ketone. You are getting a byproduct here of the ethyl copper. All right. Now, the next reaction that we want to consider is, this is, as we were counting before on the list, I think was number 3, the reduction of carboxylic acids and derivatives. Now, if you think about it, we recently talked about reduction of aldehydes and ketones. Those are going to be related processes. Now the focus is on reduction of, well, we're including both now, carboxylic acids and derivatives. Now, except for amides, remember they're the least reactive, carboxylic acids and their derivatives, they all reduce to primary alcohols. That's a general pattern. So if you start out with a carboxylic acid or a derivative, but not amide, the reducing agent will react with it, produce a salt, and then you do an acid workup on the salt, and you're going to get an alcohol, right? Now, in this reaction, there are two reducing agents that are used: lithium aluminum hydride (LiAlH4) and sodium borohydride (NaBH4). Now, we've done a lot to date with sodium borohydride. I don't think we've done very much with lithium aluminum hydride. Yeah, actually, did mention it in the reduction of aldehydes and ketones. We should know that lithium aluminum hydride is about 10 times more potent than sodium borohydride, 10 times more reactive. In fact, it's so reactive you normally don't see it in an undergraduate chemistry lab because it has potential to catch fire. You have to be very careful with it. Now, lithium aluminum hydride is strong enough to affect reduction of a carboxylic acid and all derivatives, including an amide. The sodium borohydride, being less reactive, will only reduce acid chlorides. All right. Let's see here. Let's take a look at outline the mechanism using an aluminum hydride anion and an ester to illustrate this. Well, step one, it's basically the aluminum hydride donates a hydride ion as a nucleophile to the carbonyl carbon. The aluminum acts as a Lewis acid attaching to the alcohol. That's basically adding an aluminum hydrogen across the C double bond O. You still have 3 more ALH bonds that can bond to 3 more esters, and you end up with this kind of complicated looking aluminate salt. These are the carbons here is really tetrahedral. Well, the next step is the ejection of the heteroatom leaving group here, the OCH3. Now, that sometimes it has trouble doing that. If you used a very nonpolar solvent, it would have a lot of trouble. And what will make this reaction occur often is an aluminum acting as a Lewis acid. It's going to attach to this and help to pull off the O carbon group here. All right. So there's a little bit of a challenge, you see, for that heteroatom group to come off, and what will often help it is your aluminum acting as a Lewis acid. All right, when that breaks off, you have an aldehyde. Now, there's still active reducing agent around, aluminum hydride species all around. And so that aluminum hydride is going to go ahead and reduce the aldehyde to a salt, and the salt is worked up by acid to give the final alcohol product. All right. Now, you mentioned that amides are an exception. Amides are the least reactive of the carboxylic acids. They require the most potent reducing agent to react with them, which is lithium aluminum hydride. Now, interestingly, the course of the reaction is different, however. Now, before, we were always getting a primary alcohol. Right? Reduction of a carboxylic acid or a derivative would produce the primary alcohol. But now, that's not our product. We actually get an amine. And the reason we get an amine is a testament to the fact that the nitrogen is such a poor leaving group. It's so hard to break off as an amide ion. It actually refuses to break off, and so it just stays attached. We'll see what's happening down here. So, as we showed before, there's an addition of the aluminum hydride across the CO double bond, and the hydride acts as a nucleophile, attaching to the carbonyl carbon. Aluminum is a electrophile, a Lewis acid bonding the oxygen. Now, ordinarily, this heteroatom group would be pushed off, would be ejected. But it's so terrible a leaving group, it refuses to break off. Instead, what it does, it countervenes, and the lone pair from the nitrogen actually is pushed in, and it in fact breaks off the oxygen aluminate group, right? And that's actually the next thing that happens. That produces, when that lone pair swings in and kicks out the aluminate as a leaving group, you get this. Remember this positive CN double bond called an iminium ion. Now there's still reducing agent around. The aluminum hydride is going to donate a hydride ion to the carbon here, and boom, that produces your amine product. Right. One way to look at this pattern-wise is that everything attached to nitrogen, that doesn't change. The CO double bond is effectively reduced to a methylene when all is said and done, when you do the whole, go through all the steps and the final workup, reducing the C double bond O to a methylene. All right, now, every time I talk about this, I have to appreciate the actual ingenuity of organic chemists. They must have been sitting around thinking to themselves, thinking about the detailed mechanism that we just outlined for reduction. Organic chemists have come up with a couple of designer reducing agents, and requiring some spatial conditions that if you take, this works with an acid chloride and an ester, and you react it with one of these spatial designer reducing agents, you get reduction, but it's different than before. It actually, the reduction product is an aldehyde, not a primary alcohol. Now the two designer reducing agents are diisobutyl aluminum hydride. Here's its structure here. It's helpful to abbreviate that one. You can say di-val-H. Di-isopropyl butyl aluminum Al, and then hydride. Notice there's just one hydride ion here. With the, let's say, aluminum hydride, there was, aluminum hydride would be 3. The lithium aluminum hydride, there's 4. Second, this is a variation of lithium aluminum hydride. If you start it with lithium aluminum hydride, LiAlH4, 3 of the hydrides are replaced by tertiary butoxy groups. Right, now tertiary butoxy groups, those are those large oxide groups. And you abbreviate that here, that's LiAlHOTBU. Now, the world needs actually an acronym for the designer agent number 2. For number 1, it probably has its own acronym, di-val-H. It doesn't exist for number 2. I think I've suggested to students, maybe you can, if you can think of a cool acronym, let us know. I've come up with some dumb ones, and they're so dumb I didn't put them. But anyway, I want to explain now. Well, let's look at the overall reaction, and you can see here what's happening, and then we'll get into the explanation. Now, the 2 substrates that you're going to require are the acyl chloride and the ester. Now, they're treated either with reducing agent number 1 or number 2. A couple of conditions you do require, though, are low temperature. We'll explain why in a bit. Minus 78 degrees Celsius. That's basically dry ice temperatures. And then a nonpolar solvent like toluene. All right, there's a salt that's produced, and you do the acid workup, and boom, you'll get an aldehyde here. So, what's happening? Well, I'm going to explain, but there's a number of factors that come into play. One of the main ones is that these designer reducing agents, if you examine them, have large, bulky groups attached to the aluminum. You see, they basically they have steric hindering groups. And that steric hindrance is going to play a role in making this reduction happen the way that it does. The 2 isobutyl groups here, 2 large bulky groups, and the 3 tertiary butoxy groups. Those are all big, bulky groups. Now, first of all, to explain all this, let me give you a simplified view of the reduction mechanism that would involve a normal, unhindered hydride agent, either sodium borohydride or aluminum hydride. Alright, so this is the way the reduction works normally if you use this lithium aluminum hydride, sodium borohydride. The hydride ion acts as a nucleophile, bonds to the carbon. It produces this tetrahedral intermediate. It then ejects the leaving group to give the aldehyde. There's still hydride ions around from the reducing agent, and the next step is a hydride ion from the reducing agent, then it nucleophilically attaches to the carbon, the carbonyl carbon of that aldehyde. And then the basic at this point, it's a salt. It's a borate or aluminate salt, and it stops there. What you do is the acid workup. The acid workup basically attaches a hydrogen ion to the O-, and you get your alcohol here. All right. Now, reducing a carboxylic acid derivative to an aldehyde through those use of the designer reducing agent, it works for really three reasons. First of all, the low temperature, -78, the fact they're using a nonpolar solvent toluene, and the sterically hindering groups of the reducing agent. And right now, the key is this, is that the designer reagents are going to cause a addition across the C-double bond O, as we saw before. And we have basically a tetrahedral intermediate here. Now, ordinarily what would happen is this L group, the heteroatom group, would break off, but it has trouble because the temperature is so low, and also there's toluene solvent. Breaking off as an anion, that wouldn't be very stable in the nonpolar solvent. Well, it's still got an option for reaction, and it's this, that what could happen then is a neutral aluminum species, there's going to be some in equilibrium, even with the lithium aluminum hydride, and it acts as a Lewis acid that basically bonds to the leaving group and helps to pull it off. Well, when you use one of these designer reagents, they've got large, bulky groups in here. They're so big and bulky, they will sterically hinder this aluminum from getting close enough to latch on to the leaving group and help to pull it off. That's the other key of how this works. These large, bulky, sterically hindering groups prevent a second aluminum from latching on to the leaving group in the tetrahedral intermediate and prevent it from pulling it off. If it did, you'd get the aldehyde, which is in the environment of hydride donating agents. The hydride agents would reduce the aldehyde. So what happens now is it basically stops at this stage right here. All right, it forms this tetrahedral intermediate stage. It doesn't react further. Now, when you do the basically the acid workup, everything hydrolyzes away. We're showing that in this slide. The tetrahedral compound at this stage here, that's the end product when you do acid workup. Now, the acid workup also would destroy any excess reducing agents, hydride reducing agents, and so it's going to quickly react, go away. And then hydrolysis of the aluminum oxygen bond here takes place, and you're going to now, in this aqueous acid environment, eject the leaving group, and there's your aldehyde. All right, and you see this is not further reduced because all the hydride donor species are gone. They'll react with the acid that you're adding in the acid workup phase. So that's how basically that reaction works. It's a good reaction, it goes in high yield. All right, I want to just talk about two more reactions of carboxylic acid. And this is number 4. This one's an interesting one. It's called decarboxylation. I can't tell you how important a process that is. You and I wouldn't be alive if it weren't for a cellular level decarboxylation that naturally occurs. In the Embden-Meyerhof glycolysis process, there's a number of instances where decarboxylation occurs. In the citric acid cycle, there's a cycle of 8 species traveling in a circle around and around, and there's a couple of reactions there that involve decarboxylation. Decarboxylation is the conversion of a carboxylic acid, the fragmentation of it, the elimination of carbon dioxide from that. Well, chemically, when I talked about the decarboxylation citric acid cycle, that's partly where you're getting the carbon dioxide that basically goes to the lungs and we breathe it out, right? Well, in the laboratory, decarboxylation is really a tough process. You can't just take any old carboxylic acid and do the decarboxylation, elimination of CO2. Biochemically, there's an enzyme cofactor system that makes it all happen. But if I just take, for example, this an ordinary carboxylic acid, well, you're going to have a tough time decarboxylating it. What I want to stress here, though, is there is carboxylic acids, if they have certain activating groups on them, and you heat them to high temperature, they will decarboxylate you. Now, I talk about activating groups. Look at these groups. Pay attention to them. They're so important. I even give them a spatial category name. The C double bond O, the nitro group, and the CN. It's not written on the slide here, but I call those the 3 amigo groups. I do that because that makes a big deal of the 3. They're really important. We'll see them again back in the next chapter, chapter 22. But the idea is this, is that if you have a carboxylic acid and either of these 3 groups are attached to the so-called alpha carbon. Alpha carbon is the next door carbon. You've got your carboxyl group and then the adjacent carbon, you call that the alpha. If you had other carbon in the chain, the next one would be beta and then gamma and so forth. The key for this decarboxylation to happen, for the carboxylic acid to be activated and undergo decarboxylation when it's heated, is to have one of these 3 amigo groups attached to the alpha carbon. Here we have a ketone carbonyl group attached to alpha carbon. If you take this and heat it, we're talking about probably 180, 200 degrees Celsius. It will break off carbon dioxide, and this ketone is the byproduct. All right. Now, how do these activating groups work? All right. Let's take a look. This beta keto carboxylic acid that we mentioned. Well, the key is this, that the most stable conformation for a compound like this is where the carboxyl group kind of wraps around and internally hydrogen bonds with this oxygen here. You'd have the same kind of effect with a nitro group and even a cyano group. There'd be this internal carboxyl group reaching around and forming an internal hydrogen bond. This is a stable species because it's a 6-membered ring and because it's got an extra hydrogen bond right there. This would be the conformation, the stable conformation that this compound would exist in. Now, of course, it would just sit there. However, if you heat it, all the atoms are poised to undergo this decarboxylation process, which is, in fact, it's a bond-making, simultaneous bond-making, bond-breaking process, and we try to break it down here. Upon heating here, this acid strength increases enough that it can attach a proton to this oxygen. It's going to pull away a pi electron pair here, creating a positive charge there. As this hydrogen is donated to the carbonyl oxygen, that produces a negative charge here that's going to try to push in and form a C double bond O. You've got that push here. You've got the positive charge that's going to pull on the electron bonding pair electron here. So there's a whole bunch of push, pull, resulting in kind of a flow of electron pairs, resulting in bond making, bond breaking. Again, this is it's not so energetically easy. It requires high temperature, but with high enough temperature, that will make all this happen. And as the bonds make and break, let's see what we're going to get. Well, H donated to that. This double bond goes to single. The electron bonding pair swinging over forms a CC double bond right there. And fundamentally, you're breaking this bond right here, and you're forming a CO double bond. That's how the carbon dioxide gets formed, and it, of course, diffuses away. Okay, now if I were giving little award points, I would ask the question to see if you can remember what you call this, and we've seen it actually. I can't count the times. A couple times we're going to see it more again. This is the famous enol. We saw it first in first semester. We talked about the acid mercury catalyzed addition of water to a alkyne group. We form an enol intermediate there. Here, this enol, that's the first product that forms. Enol forms are not so stable. They tend to spontaneously rearrange to a more stable isomeric form called the keto form, and that's what happens here. The mechanism of this, that's something we commented on last semester, and we're going to come back to this because later on, we're going to see other cases of enol isomerizing to keto form and so forth. And we'll see other things that enols do. So as I say, pay attention, you're going to see it again. All right. Now, what I have next, I want to kind of a little exercise, I guess. I've got a number of carboxylic acids in this group and this group. If this were in the form of a question, if I were doing a whiteboard discussion, I would put this as a class exercise. I could have done that in a video, I just didn't have time. But the question is, which of these carboxylic acids is susceptible to decarboxylating when they're heated? Always heating to high temperature. Whether that's called a thermal decarboxylation. It's promoted by high temperature, thermally promoted. All of these carboxylic acids will decarboxylate when heated at high temperature, whereas these two will not. Now the key again is that to have one of the three amigo groups bonded to the alpha carbon. And so let's take a look at these. Here you have an amigo group, the nitro, bonded directly to there it is, alpha carbon. Therefore, we have to say a big yes. This will decarboxylate when you heat it. What about over here? Well, there's the alpha carbon, and you got a cyano group. That's one of the three amigo groups, and so yeah, that one's going to decarboxylate upon heating. What about here? There's the alpha carbon, and that's directly attached to a carbonyl ketone amigo. So yeah, this one will decarboxylate. What about that one? It says it will. Do you see why? Well, this might be trickier to examine because I've written the carboxyl groups as in their abbreviated form, CO2H. Each of these has a carbonyl group and an OH. All right. So with respect to this one, let's say carbonyl group and OH, the carboxyl group that potentially gone to decarboxylate, break off CO2. The other carboxyl group has a carbonyl group, and that carbonyl group, of course, is attached to the alpha. So yeah, this is going to be vulnerable to thermal decarboxylation. Now, these two, we're saying do not. Let's see why. Well, there's the nitro group, but you'll notice it's not directly attached to an alpha carbon, it's attached to a beta carbon, so it's a big nopers here. It won't decarboxylate on heating. Now this one has fooled many a attentive student, and it won't either, because you see the alpha carbon is the carbonyl group. The carbonyl group can't, an amigo group can't be the alpha carbon. It has to be attached to the alpha carbon here. So this will not decarboxylate. Right. Finally, there's one more reaction that I want to discuss. This is number 5. It's a name reaction. Many of the important reactions in organic chemistry bear the name of their discoverer developers who have already seen that. This one is called the Hell-Volhard-Zielinski reaction, or for short HVZ reaction. And one uses either chlorine or bromine. You use a carboxylic acid mixed with either chlorine or bromine, a trace of phosphorus, and it affects alpha substitution on the alpha carbon. And it's a good reaction, goes in high yield. Now, kind of put this in context, we have looked at other halogenation reactions. One that might compare with this is that if you have an alkene, you can do halogenation in the so-called allylic position. That's the carbon directly attached to the alkene. If you have an arene, that is an alkyl attached to an aromatic ring, and you use, one of the, you can use halogen and white, or you can use one of the designer allylic or benzylic halogenating agents. You get attachment of the halogen on the alpha carbon of that group. Here you're attaching halogen to the alpha carbon with carboxylic acid. Now, the mechanism gets complicated. I don't want to go so long in this video. I may come back to the details, but I'll let you kind of examine it. And here it is. There's a whole lot that happens. That's the mechanism of it. But I don't want to overtax people's thinking on this right now. So we'll potentially can come back to that. But the reaction is a good one, going in high yield, and it's a very useful reaction. So that's all we'll do today. Probably next week in the video, I might just do some touch-up things with respect to carboxylic acids and their derivatives. Well, I definitely will. There's a few little things I want to touch base on, and then we're going to start chapter 22. And let's see, we'll be posting, the class notes. I don't think I've done it yet, in chapter 21 and the assignments. And you get past the exam, and hope you all do on that well, and you realize you get 2 attempts on that. Then you can turn attention to studying the chapter 21, carboxylic acids and their derivatives. Okay, that's all, and thank you for watching.